We will begin Unit 4 by looking at radicals and square roots. So what I've written here next to my first bullet point is the square root of 9, and this fancy symbol here is called the radical sign. And when you see the square root of a number, that square root is asking you a question similar to the way a logarithm asks a question. The question here is, what number squared equals 9, or whatever number is under the radical sign? So in this case, what number squared equals 9? Well, I know that 3 squared equals 9, so the square root of 9 must equal 3. This positive number, this square root that we found, we call that the principal root, okay? The positive square root is the principal root. Now you might be thinking, what is she talking about, the positive square root? Well, you should notice that there is another square root of 9, and that is -3. Because if you take -3 and you multiply it by itself, negative times negative is a positive. So -3 times -3 will give you positive 9. So another square root of 9 is -3. Okay, that's something to keep in mind. Okay, on the other hand, we cannot, at this point in the course, have a negative under the radical sign, okay? We'll be dealing with that in the second topic of Unit 4. But the square root of -9, well, there is no real number that satisfies our question, okay? There's no real number that when multiplied by itself yields a negative number, okay? -9 has no real square root. If you think about that, you can take 3 times 3 and you're going to get positive 9. You can take -3 times -3 and you're still going to get positive 9. Now you might be thinking, oh, well, a positive times a negative is negative, and yeah, that's all well and good, except a positive times a negative, you're not multiplying the same number by itself, okay? 3 times -3, you're not squaring 3 at that point, you're just multiplying two different numbers. So there is no number that when multiplied by itself gives you a negative number, nonetheless -9. So this kind of negative thing, we'll talk a little bit more about this at the start of Unit 2, but I did want to make a note in case you were wondering at this point. So one of the problem types that you might see in your assignment or in your Check for Learning quiz is something like this. Find 2 square roots of 49. So the square root of 49, well, 7 times 7 is 49. 7 squared is 49. So 7 is the square root of 49. And also -7. -7 times -7 will give me a positive 49 as well. So my 2 square roots of 49 are 7 and -7. Okay, one other thing I do want to show you is that not all radicals are square roots, okay? So this says evaluate here. I forgot to write out my instructions longhand here. If I were to evaluate this radical, we have a tiny little 3 out front, okay? The 3 is small and it's kind of sitting in the radical. What this means is it's the cube root, and it's asking the question, what number raised to the 3rd power? What number raised to an exponent of 3 equals 8? Okay, so the square root says what number squared or raised to the exponent of 2 equals a number, in this case 9. This is asking what number raised to the 3rd power equals 8. Well, 2 times 2 is 4, times another 2 is 8. So 2 to the 3rd power is equal to 8. So I know that the cube root of 8 is equal to 2. You can, in fact, take a root of any number that you want, and you can take whatever number root that you want as well. I could take the 4th root or the 5th root or the 27th root. Okay, all of those things would just say, well, what number raised to the 4th, 5th, or 20, whateverth power equals the number under the radical. All of that gets a little bit, scary looking with that big radical sign. So we have another way that we can represent. That is rational exponents. Radicals can be expressed as fractions in exponents in the following way. So I've written out a bunch of examples for you here. This is just another notation for radicals. Radicals are equivalent to exponents that are fractions. And you want to be familiar with going from radical notation to exponent notation and back. Okay, there will be problems in your problem sets that require you to write a radical as a rational exponent and a rational exponent as a radical. So in this first one here, the square root of a, I'm just using a because we could put any number in here and the format would still be the same. The square root of a is equal to a to the power of 1/2, okay? So we have an exponent that is a fraction, and this 1/2 means take the square root. All right, let's look at another one. The cube root of a is equal to a to the power of 1/3. The fifth root of a squared, okay, now we've got an a squared in here. This will be equal to a to the power of 2/5. So the exponent on your number inside the radical, that's going to be your numerator or the top of your fraction in your exponent. And your 5, that's the number root that you're taking, that's going to be the denominator or the bottom of the fraction in your exponent. So you want to get used to kind of where these numbers move around and how this notation works. Okay, similarly, the 8th root of a to the power of 7 is equal to a to the power of 7/8. Okay, once again, this whole fraction is an exponent on that letter a. And these are equivalent, okay? Either one means the exact same thing. So you might want to practice, jot down some examples for yourself, see if you can convert them back and forth, and kind of familiarize yourself with that notation. One very cool thing about writing radicals as exponents is that we've already studied the properties of exponents. And because radicals are essentially a certain type of exponent, well, we've already studied the properties of radicals. So radical properties are inherited from the properties of exponents. These will look very familiar to you, which is part of the reason why this video gets to be shorter than the videos of the last few weeks, because you really see how this knowledge is building upon itself as we move forward. So let's get into it. Radicals distribute over multiplication. So if I have two numbers multiplied together under a radical, so here I have 9 times 4, and I'm taking the square root of both of those, or that whole multiplication thing going on in there, okay? If I have this type of situation with multiplication, I can just write this as the square root of 9 times the square root of 4. So it's okay to kind of break apart this radical, or this square root, and distribute it to the 9 and to the 4. Okay, remember that was true also of exponents, okay? If you had an exponent of two things that were multiplied, you could distribute that exponent to both factors that were being multiplied. So that's the same thing happening here. 9 times 4, this whole thing is being raised to the 1/2 power. So there's no reason why we can't say 9 to the power of 1/2 times 4 to the power of 1/2. And you'll see here, if we evaluate that, the square root of 9 is 3, the square root of 4 is 2, so 3 times 2 is equal to 6. And just to kind of prove this to you, why this property works the way it does, well, we get 6 if we kind of solve this another way. If we multiply the 9 and the 4 first and get 36, well, the square root of 36 is 6 as well. So you can kind of keep this in your mind that this works as a property. It's a rule that governs radicals and multiplication. Okay, radicals also distribute over division, because remember, division and multiplication are related. So if I have the square root of 16 divided by 4, well, I can take the square root of the top and the square root of the bottom, and that is an equivalent expression. So square root of 16 over 4 is the same as the square root of 16 over the square root of 4. If I were to evaluate that, the square root of 16 is 4, the square root of 4 is 2, 4 divided by 2 is 2. And on the other hand, well, that makes sense, because 16 divided by 4 is 4, and the square root of 4 is 2. So that's kind of a little evidence to prove to you that radicals do distribute over division the same way that exponents do. Another property is that fractional exponents raised to more fractional exponents multiply, okay? So here we have 6 to the power of 7 over 14. This is our first fractional exponent, and we can raise it to another fractional exponent, 2 over 3. You could write this in radical notation. It would look like a radical inside of another radical, and those values, those fractional exponents, will multiply. So we can take 7 times 2 and 14 times 3. That gives us 14 over 42, which simplifies to 7 over 21. You may have noticed that you had common factors on the top and the bottom. When you're multiplying here, you could probably cancel out this 2 to a 1 and this 14 to a 7 and get right over here to the 6 to the power of 7 over 21. Okay, if you saw that, great. If not, it doesn't matter. It's just one more step. But yeah, so these fractional exponents raised to more fractional exponents, they work just the same as any old exponents. When you raise an exponent to another exponent, the exponents multiply. The final property that we're going to look at is just like variables that have exponents. Like terms with radicals combine through addition or subtraction. That's kind of hard to write out in a way that makes any sense, so I think you kind of just have to see it. Here's an expression, 8 square root of 2, so this is, one number, okay, minus 5 square root of 2. And these are, in some sense, well, in a very real sense, they are like terms because they both share this factor of the square root of 2. So you can kind of think of this for a second. If this square root of 2 were an x, most of you would feel very comfortable with that. You'd say, oh, 8x minus 5x. Well, that's 3x. They're like terms. I can subtract them. That's fine. The same thing is true when you have a radical here. So 8 square root of 2 minus 5 square root of 2, we can subtract the numbers out here. You can think of it like a coefficient, or this outside factor, and then just keep what's under the radical. This is kind of taking the place of the variable in the binomials that we're used to seeing. So this is equal to 3 square root of 2. So just be familiar with that idea that you can combine like terms as well. You can also think of this kind of like reverse distribution, I guess. But since we know all of the numbers, it turns out it's just this one nice number over here, 3 square root of 2. So I realized we moved very quickly through the properties of radical expressions because they are inherited from the properties of exponents. But I do want to show you some examples of how we can apply these properties to the types of problems that you will see in your assignment and your Tech for Learning quiz. So the first example here says to multiply, and we're supposed to multiply the square root of 11 times the square root of 5. Now remember that radicals distribute over multiplication. We can move them around kind of any which way we like. So I can consider this to be 11 times 5 under the radical, okay? And I know that 11 times 5 is 55, so the square root of 55 will be my answer. Okay, another thing I can do is I can simplify by factoring. So here's another set of directions, and I'm supposed to simplify the square root of 360 by factoring. Now, when I'm simplifying by factoring with square roots, what I want to do is I want to look for factors that are perfect squares, okay? Factors that have nice, easy square roots. Okay, so 360 has a number of factors, okay? 2 is a factor, 5 is a factor, all kinds of factors. But I want to think of a factor, preferably the biggest factor I can think of, that is a perfect square. And the one that comes to mind is 36, okay? 360 is equal to 36 times 10 if I were to factor it into 2 factors. So I can break apart this 360 into 36 and 10 under my square root. I can now kind of break apart this square root using my multiplication property. This is the same as square root of 36 times the square root of 10. And the square root of 36, well, that's just 6. The square root of 10, however, doesn't have a nice, easy square root solution, and it can't be simplified anymore by factoring because no factors of 10 are perfect squares, right? Let's see, 1, 2, 5, okay, those are 10, those are the only factors of 10. None of those are perfect squares. So this is as simplified as we're going to get. 6 square root of 10 is our answer. Another type of problem you will be asked to do is to do something very fancy sounding called rationalizing a denominator. So when you're asked to rationalize a denominator, what you want to do is you want to get the square roots out of the denominator, or get all of the radical signs out of the denominator. It's okay if they hang out on the top of the fraction, but we don't want to see them on the bottom of the fraction. This is just a mathematical convention. It makes things much easier to work with when they're rationalized in the denominator. So if I had this radical right here, the square root of 11 over 7, I'm asked to rationalize the denominator. So the first thing I'm going to do is I'm going to break apart this square root on the top and the bottom. I'm going to write this as the square root of 11 over the square root of 7. Here's where the magic of rationalizing a denominator happens. To get this square root out of the denominator, out of the bottom of the fraction, I'm going to multiply the top and the bottom of the fraction by what's on the bottom of the fraction, okay? So if I multiply this entire fraction that I have here by the square root of 7 over the square root of 7, I haven't changed the fraction because I'm multiplying by the same thing on the top and the bottom. So really what I'm doing is I'm multiplying by a factor of 1, which doesn't change anything. So that's great news. Okay, let's see. Let's multiply across square root of 11 times the square root of 7. Well, I can just multiply the insides here, 11 times 7 under the square root. And here on the bottom, square root of 7 times square root of 7. That's the same thing as the square root of 7 times 7. Let's do this multiplication. 11 times 7 is 77. 7 times 7 is 49. And here is where we get that square root out of the bottom of the fraction. The square root of 49, we know what that is. It's a perfect square. It's just 7. 7 doesn't have any radical signs or square roots. So we are successfully, we have successfully rationalized the denominator of this fraction. What we're left with on top is still the square root of 77. 77 doesn't have any factors that I know of that are perfect squares. So this is as simplified as we're going to get. And thankfully we've gotten our radical out of the denominator, so we have rationalized the denominator of this fraction. Another thing you will be asked to do is to subtract and simplify when you have radicals involved, or to add and simplify, I suppose. It would all work the same way. So if we had something like this, 3 square root of 48 minus 8 square root of 3. Now remember, you cannot add or subtract unless you have a common factor or like terms in a certain sense. So 48 under the square root and 3, well, those aren't the same thing. So we can't just go ahead subtracting at this point. What we have to do is we have to make what's under the square root look the same in both terms. So 3 is smaller, so I'm going to work with the larger number and see if I can get a 3 out of here. I want to ask myself if 3 is a factor of 48, because if it is, then that's just great news. And I think it is. 48 is equal to 3 times 16. So I can break apart this 48, I can factor it. I've done that here in the next line. I've taken 48 and I've rewritten it as 16 times 3. So I've rewritten this expression, 3 square root of 16 times 3 minus 8 square root of 3. Now I can break apart this radical here using the multiplication property. 3 square root of 16 times square root of 3 minus 8 square root of 3. And the square root of 16, lucky us, square root of 16, that's a perfect square. It is 4. So this is 3 times 4 square root of 3 minus 8 square root of 3. And 3 times 4 on the outside, these are outside of a radical, so they can just multiply by each other. That is 12. 12 square root of 3 minus 8 square root of 3. Now this looks good. These look like the like terms that we were talking about before. We have a common factor of square root of 3 and square root of 3. We can combine these the way we combine like terms. 12 minus 8 is 4, and we keep the square root of 3. Like I mentioned before, you can think of this as if you're pulling out a common factor. Okay, I'm pulling out the square root of 3 in each term, and I'm leaving the 12 minus 8. And I know 12 minus 8 is 4, so I have 4 times the square root of 3. This would be my solution when asked to subtract and simplify these two terms. I have one more type of example for you. In this one, the instructions just say, once again, to multiply. And we have this fancy looking expression here, 6 plus the square root of 7, this whole thing squared. So when I'm squaring anything, I'm multiplying it by itself, and this square is applying to everything in parentheses. So I'm going to take 6 plus square root of 7 and multiply it by itself. So here in this next line, you can see that I've written it out twice. 6 plus square root of 7 times 6 plus the square root of 7. Now, when you multiply this out, remember back a few units, you're going to multiply every term by every other term. So 6 times 6 is 36. 6 times square root of 7 is 6 square root of 7. Square root of 7 times 6 is 6 square root of 7, and square root of 7 times square root of 7. I'll just write those next to each other in my final term for now. Okay, I'm going to simplify these guys. 36, he's the only number without a radical, so I'll leave him be for now. 6 square root of 7 plus 6 square root of 7. Well, I have the square root of 7 in both terms, so I can add the 6's. That gives me 12 square root of 7. And the square root of 7 times the square root of 7, that's the same thing as the square root of 49, which happens to be a perfect square equal to 7. So I just get a 7 out of this last term. Now I have 36 and 7. I can add those together. That gives me 43. And this term with the radical will just stay the same, 12 square root of 7. Now at this point, I've combined all of my numbers that don't have a radical sign, and everything under the radical, under this square root, is, well, as simple as it's going to get, because 7 doesn't have any factors that are perfect squares. So it looks like I have successfully multiplied and simplified my result.